Assalamu alaikum and welcome to lecture number 8. In this lecture we'll be talking about the downsampling, upsampling and rational rate conversion. So you were on this slide in the previous lecture. So you understand what does downsampling means. Downsampling means to throw away the sample. So if we downsample a signal by a factor of say m, then we are throwing away m samples, right, consecutive samples from the discrete time signal. To get clear understanding of this, let's first see let's take a numerical example and see how the downsampling actually is. So for example, we have a signal, right, x prime of n, which is downsampled version of x of n, and the by a factor of m, right? So that means we are throwing away m samples from x of n to obtain x prime of n, right? So for example, let's consider the following signal. So we have original signal x of m, and we assume that we want to downsample it by a factor of 2. So in that case, we are throwing away each of the alternate samples. So that means we are throwing away, right, we are taking m equals to 2. So when m equals to 2 means that we are throwing away one sample, right, from okay. So originally the samples were here in this x of n. We have samples, these samples, right, this is your x of n, and x prime of n is drawn here. So you can see that we have sample here. So the sample at 1 is throw away. So we have the next sample here, 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 and you can also check that the sampling period is increased, right? So here the sampling period, for example, it was t of s. So here the sampling period, which we represent by t prime s, now this is equals to 2 times the t of s, right? So you understand sampling period and sampling frequencies are reciprocal. So if that means here we have increased the sampling period, so that means the sampling frequency, which we represent by omega prime s, that will be equal to half of the sampling frequency which we have here. So that means omega prime s equals to half of the omega s. And you understand what happens when we reduce the sampling frequency, right? So you understand by Nyquist criteria, if sampling frequency is equal to or greater than 2 times the highest frequency present in the signal, right? So for example, highest frequency present in the continuous time case is omega m. So if this condition is met, then we can reconstruct the signal, otherwise we cannot. So that means in the resulting signal, which is downsampled, will have sampling frequency, which is, because in this case we have taken m equals to 2, so the resulting signal x prime n will have the sampling frequency which is half of this signal sampling frequency. So if in the original case, this one, the sampling frequency is, for example, 4 times, right, because it is inequality. So for example, in the original case, if the sampling frequency is 4 times omega n, right, so in this case it will be the sampling frequency omega prime m, which is equal to half of the omega s, right? So if we have sampling frequency 4 times here, then there will be the omega prime s will be satisfying the equation like this. Omega prime s will be just equal to the minimum required frequency. Okay, so that means it will be equal to basically 2 times omega n. So in this case you understand there will be no aliasing. But in case if here the sampling frequency is just equal to twice of the maximum frequency, then if we reduce the sampling frequency by half, that means there will be aliasing distortion. So we assume that there is no aliasing in xn, right? So that means aliasing was xn was sampled using the Nyquist criteria, that is the sampling frequency in this case is higher than the 2 times the maximum frequency present in this signal. Now if we downsample the signal, on the previous slide you see that if we downsample a signal by 2, that means you are halving the sampling frequency. So in this case the sampling frequency is reduced for the downsampling by a factor of m, so that means you are reducing the sampling frequency by a factor of m. So the new signal produced x prime n will be slower, so there might or might not be aliasing in x prime of n depending upon the highest frequency present in x prime of n and the sampling rate. So if it meets the required criteria of the Nyquist, in that case there will be no aliasing. But if it doesn't meet the criteria, then it might contain the aliasing, right? So let's see what is the spectrum of x prime n. So we know x prime n, x prime e power j omega equals to 1 over t prime s, and summing over L running from minus infinity up to infinity x of a, this one, right? So now because you understand that we have downsampled it, so that means we have increased the sampling interval by a factor of m, so t prime s equals to mt, right? So we can write, I hope that's quite straightforward. So this one, now if we replace the variable of summation, which is L, by I plus km, so that means we can write it like summation 1 by m summation I running from m minus 1, that is a new sample that we are going to throw away, right? And this is equal to 1 over tx, k running from minus infinity up to infinity x of a. I hope that's quite straightforward. So by simple mathematical manipulations we can obtain this one. So that means the mathematical description for the signal that is downsampled, before downsampling it has mathematical description as, so that's the expression or the discrete time Fourier transform for the sampled signal. And if we combine the similar term, that is omega by mts, and that's also 2 pi by mts, so if I combine them I get x of a omega minus 2 pi I by mts and minus 2 pi k by ts, right? So if we compare this one with this equation, we can say that basically omega is replaced by omega minus 2 pi I upon m, right? So that means in terms of this equation we can write it like this. So that's the expression for the downsampled version of the signal, okay, in frequency domain. So that means if we replace omega by 2 pi I over m and we sum it I running from 0 up to m minus 1 and also scale it by this, so we get the expression for the downsampled signal, which is x prime of ej omega, and it is downsampled by a factor of m. So that's the expression in terms of x of ej omega. This shows that spectrum, the downsampled signal, contains copies or images of x of ej omega that are shifted by integer multiple of 2 pi, right? So if you look at the original one, we have omega by ts, but now instead of omega by ts, now we have omega minus 2 pi by 2 pi, right, times ci, and it is also scaled, that is stretched by a factor of m. Okay, this intuitively justified as well, since the signal is compressed in time, it should stretch in frequency. So if images in the x prime of ej omega overlap, then there will be aliasing distortion, right? Otherwise, if images do not overlap, then there will be no aliasing. So to ensure that there is no aliasing effects, then we use a low pass filter before the downsampler. So the combination of the low pass filter and the downsampler is called decimator, right? What will be the cutoff frequency of this low pass filter? To find the cutoff frequency of this low pass filter, let's write again the equation for, so if omega, the frequencies in the input analog signal is band limited to omega s prime by 2, then there will be no aliasing. So let's calculate. So let's assume that we have the input signal frequency, which contains the highest frequency omega n, and 2 times omega n equals to omega prime s, right, which is the sampling frequency, right? So if it is equal to 2 times of this one, that means there will be no aliasing, because according to Nyquist rate, Nyquist criteria, the maximum frequency, twice of the maximum frequency contained in a signal should be equal to or greater than the sampling frequency. So if you have sampling frequency represented by omega prime s and it satisfies this condition, then we can say that omega maximum of the frequency omega n equals to omega prime s by 2. Now, because we know omega prime s is equal, the relationship between omega prime s and the period is that this is equal to 2 times pi divided by the sampling period, which is represented by omega prime s. So in that case, we say, okay, this is equal to 2 times divided by, right? So that's already 2 here. So because we have this thing, right, this relationship, that is omega prime s equals to 2 pi by ts. So replace value here, so that will be ts prime. So that means we cancel the 2 and we get the maximum frequency equals to pi by ts prime. I hope that's clear. That's your maximum frequency. Okay, now the relationship between ts and ts prime is that we know, because we are downsampling it. So that means the ts prime is basically m times the t of s, right? So if we replace here, we get so that means let's represent the omega n, the maximum frequency, by omega. So we say, okay, omega equals to m by mts. Okay, so I have written here. Then we say, because the relationship between the angular frequency of the continuous time signal and the discrete time frequency of the discrete time signal are related by this equation, that omega equals to omega into ts. So putting the value of omega equals to m by mts. So that means ts cancels with ts, so we get omega equals to, that's the maximum frequency, equals to m by t, right? So if we use this as cutoff frequency, right, let me write omega c so that you understand this is basically cutoff frequency. You can also say that's a maximum frequency, right, which we have for the non-aliasing case. If the frequency increases beyond this, then we will have the aliasing, right? So to avoid aliasing, we can have maximum frequency equal to this one. So if I use a low pass filter with cutoff frequency of this one, then we can avoid the aliasing and the resulting down sampled signal. Okay, so you understand that's this one is called the decimator. And what is decimator? Decimator is simply a low pass filter followed by a down sampler, right? So I hope this gives you idea. Now to write it mathematically, we understand that this is our input signal and we want to downsample it by a factor of m. So before downsampling, we put a low pass filter so that we can avoid the aliasing, right? Now because that's ideal low pass filter, so what this is the response of the ideal low pass filter in the frequency domain. So to find the response of the ideal low pass filter in time domain, which we call it impulse response, so we can use the inverse Fourier to find the impulse response of this frequency response, right? So you understand it will be a sinc function, right? And in time domain we say the output, right, y of n, which is this one, so the output equals to, in time domain we say input convolve with the response of this system, right? So let me represent it by hn. So output equals to y of n, equals to y of n, and y of n equals to x of n convolve with h of n. Or we can also write in the convolution sum formula. So we say summation k running from minus infinity up to infinity. I hope this is very clear to you because this thing you have done so many times in the signal system, right? So that's the expression, right? So understand we have h of n minus k, and because h of n minus k is basically impulse response, right? So impulse response for the case of ideal low pass filter is basically a sinc function, so we can write it like this. So I hope this gives you idea. So we represent all these things graphically on the next slide. So that's your original continuous time signal or analog signal represented by x subscript of a into omega. So that's its frequency response. You understand that's your continuous time signal. So this is your continuous time frequency variable, capital omega. And if you look at this one, so it has maximum frequency omega b. Okay, now you understand. I think it was the first topic that we studied about the sampling the continuous time signal, right? So when we sample a continuous time signal, we basically, if we look in the frequency domain, we see it is basically producing replicas of the Fourier transform, right? So, and which are about around omega s, right? So we have first replica here, then we have another replica that's around omega s, then omega 2s, omega 3s, and similarly minus omega s, minus 2 omega s, and so on, right? And once we convert, replace omega s by, so we have this relationship between the continuous time signal frequency and the discrete time signal frequency. So simply it is the scale version, right? And scaling is the sampling period. So if we multiply the two, we get the discrete time signal frequency, and that's basically omega s into ts. That's the result into 2 pi. So in case of discrete time frequency, right, we have those replicas around 2 pi, right? So we have the first replica around here, then around 2 pi, around 4 pi, 6 pi, and so on. Or if we come to the negative axis, so we have around minus 2 pi, minus 4 pi, and so on. So that's what we see, and it's also scaled by a factor of 1 by ts. So that's what we see in the discrete domain, right? So for the discrete time Fourier transform, we have this thing. Now if we sample this signal, downsample this signal by a factor of m, right? So in that case we further have scaling, that is originally it was 1 by t, now it will become 1 by mts, as from the discussion on the mathematical description what happens mathematically. So if you look at that equation, you can easily see that it's basically previously it was 1 by ts, now it is, because we have sampled it by a factor, downsampled it by a factor of 1 by m. So now the scaling of this one, this is your 1 by ts prime. So 1 by ts prime equals to 1 by mts. So that's what the scaling in magnitude is happening, amplitude is happening, right? So also because we are compressing the signal, you understand from the previous example that when we downsample a signal, basically we are increasing the sampling interval. So because frequency and time are reciprocal, so that means if we are increasing the sampling interval, that means we are reducing the frequency, right? So that means previously they were wide apart, but now you see the replicas are overlapping, right? Now to overcome this problem, we propose low pass filter, right? So as from the discussion on the previous slide, so I hope this gives you idea. So once we low pass filter it, then we can remove these regions. So now you can see there is no overlap, right? Because of this there will be distortion, that is called aliasing distortion. So to avoid aliasing distortion, we should have a filter that is a frequency, right? Cutoff frequency omega equals to pi by m, right? Because we are downsampling it by a factor of m, so it's pi by m. So I hope this gives you idea. So with that we end the topic for the downsampling. Now we come to the upsampling, which is opposite to downsampling. In upsampling, we want a new set of samples x in x, right, represented by x prime of n with higher sampling frequency than the original samples. That is, t prime s will be equal to ts upon l, right? So that means we will have smaller, the t prime s is l times smaller than the ts, or in terms of frequency we can say that omega prime s is l times higher than the omega s, right? So you understand the why right? So you understand that when we decrease the sampling period, actually sampling frequency increases, and we are decreasing it by a factor of l, so it will increase by a factor of l, okay? And where l is a positive integer that is greater than 1. Note that sampling interval is l times shorter than the old sampling interval, or equivalently new sampling frequency is l times faster than the old sampling frequency. So we can write that x prime of n equals to x a of n ts prime, and because the relationship between ts prime and ts is that it is ts by l, so we have this. So we can obtain x prime of n in two steps. First, by upsampling x of n to obtain xe of n, and then low pass filtering, right, to obtain the upsampled version. So upsampling x of en is defined as x of en equals to x of n by l if n equals to 0, plus minus l, plus minus 2l, and so on. Or we can say that x of en equals to summation k running from minus infinity up to infinity x of k impulse of n minus kl. To get how it happens, let's have a numerical example. So for example, we have a signal x of n as shown here. So let's assume that we have L equals to 2. So in that case, this is your x of n, and x prime of n equals to x of n over L, right? So okay, so that means we are basically inserting L minus 1 zeros, right? L minus 1 0, right? Zeros in between the successive samples. So we'll insert 1 0 between 0 and 1, 1 0 between 1 and 2, and so on. So because L equals to 2, so that means we have 1. So we will insert 1 0 between all the samples. So if you compare, right, so that's what you get 0 1 2 3 4 5 6 7 and 8, right? So that means we have double the samples what we had here, right? So if you look at observe carefully, so you can say that the sampling interval, you see this one, is now half of what we have here. Okay, so that means the ts prime, right, ts prime is equal to ts by 2, right? So that means if we divide a sampling time by a factor of 2, means that we are basically doubling the sampling frequency. Okay, so I hope this gives you idea. So in other words, the upsampler inserts L minus 1 zeros between every 2 successive samples, so that the number of samples in XEN are increased by a factor of L. That's what we have done numerically on the previous slide. So of course XEN is not desired signal as zeros must be replaced by samples of analog signal. Hence the upsampler follows a digital low pass filter to fill in the zeros, right? So I hope you have idea, because when we were doing the reconstruction of the sample signal, so you remember that we use a low pass filter so that we can interpolate, right? So we also studied different methods of interpolation. So one of them was the ideal low pass filter. Okay, so similarly, because we are in the discrete domain, so we use a discrete low pass or digital low pass filter, so that we can assign values to the zeros we have just inserted with interpolated signal values. The characteristics of the low pass filter can be obtained by the frequency domain description of the upsampling, right? So the spectrum of the upsampling, similar to what we did for the downsampler, is xe j omega equals to summation and running from minus infinity up to infinity xe, and that's the equation for converting the time domain signal, right, into the frequency domain. So that's the Fourier equation, right? I hope you understand that's the equation for the discrete time Fourier transform, right? So from the equation on the previous slide, you know that the upsampled signal is equal to basically summation k running from minus infinity up to infinity x of k impulse of n minus kl, right? So we just replace xen here, and that's the exponential multiplier e power minus j omega as we have here in the formula. So we can simplify it as, so interchanging the summation, we can take out this one out, so we can say summation k running from minus infinity up to infinity x of k, and followed by the this expression, this one. So we have this, right? Now you understand that. So summing the impulse, right? That is, we are just summing the impulse from n running from minus infinity up to infinity, impulse of n minus kl times this, right? So I hope that's quite straightforward, that impulse is 0 everywhere except when its argument is 0. When its argument is 0, it is equal to 1, and you know when the argument will be equal to 0, when n equals to kl, right? When n equals to kl, in that case, because n can have value from minus infinity up to infinity. So when you sum it, right? So the moment when n equals to kl, so in that case kl minus kl, it will result into 0, and when it's 0, impulse will be 1. For all other points it will be 0. So I hope that's quite straightforward. So when n equals to kl, this is equal to 0, the argument is 0, and impulse becomes 1. So at that point when n equals to kl, here also you replace n equals to kl, so you have 1 multiplied by minus e j omega kl. So 1 multiplied by this will result into 1. So that means this whole thing will become into e power minus j omega kl. So we have the expression x of e j omega equals to summation k running from minus infinity up to infinity, x of k e power minus j k omega l, right? So that means, because you are summing it, if you compare with the standard Fourier equation, this equation has, instead of omega, we have omega l, right? That is, we can write it like summation, that's k running from minus infinity, you understand? That's the general equation. So that means x of k, right? And this is e power minus j, and we can write omega into l, and this is k. So if you compare with the standard equation, like we have to form the to find the Fourier transform, we say okay, summation n running from minus infinity up to infinity, x of n, right, and e power minus j omega n. So we can also sum it if I change the variable of summation. So if I replace n with k, then we have this one, right? Then here comes k, and here comes again k, right? So because here it is omega j omega, so then we say okay, this is x of j omega, okay? But now we have, instead of omega, we have omega l, so we can say this is basically omega l. So that's the final expression for the upsampler, right? The signal when it is upsampled, what is its Fourier? So it is x of e j omega l. That means we are just multiplying omega by l. So that means we have x e n has the same spectrum as x of n, with the exception that frequency is not scaled or squished, right? So you understand, because the signal in time domain is stretched because we have added some zeros, right? And then we followed by the low pass filtering. So that means we have increased some samples in time domain. We can also say that we have reduced the time interval. So that means the signal is stretched in time domain. So if something is, because of the relationship between the frequency and time, we can say that in frequency domain it will be compressed, and because it's stretched by a factor of L in time domains, it will be compressed by a factor of L in frequency domain. Also, because if x of j omega, right, if x of j omega doesn't have any aliasing, Of course, then x of e j omega l will not have, because we have increased the sampling frequency, right? But if this will have, so this depends. Okay, so in order to obtain the graph of the x prime j omega from x of j omega l, we must scale it by a factor of l and remove additional l minus 1 copies, which can be accomplished by using a digital low pass filter with a gain of l and cutoff frequency of this one, as shown in figure 5, which is on the next slide. So again, we have analog signal that consists of spectrum of the analog signal that has maximum frequency of omega b. So once we take its samples and we convert the discrete time frequency into continuous time frequency into discrete time frequency. So instead of replicas around omega s, now we have replicas around 2 pi. Okay, so we have replicas here. Now because we sample it by a factor using time sampling time of ts, so this will be scaled. That's I hope that's quite straightforward, because this we have done so many times. So it will have the maximum value of 1 by ts, or we can also say that it's basically scaled by a factor of 1 by ts. Okay, now after the upsampling, we get this signal. Okay, and after using the low pass filter, we get this signal. So you can easily observe that basically the replicas are now far away from each other if you compare with the original signal, right? Original signal means that when we haven't done any upsampling, before upsampling the spectrum is like this, and after upsampling it's this. So you can see that it is basically compressed in frequency. So overall structure of upsampler and the low pass filter is called the interpolator, as shown in the figure here. So we upsample by a factor of L, and then we low pass filter it with a cutoff frequency of minus pi by L to pi by L, right? So that's 0 to pi by L, or 0 to minus pi by L, and thus we obtain the upsampled signal, right? And we call this both, right, this as interpolator. So the output of the low pass filter can be written as, this is the input signal x of n, that's upsampled, right? So then that's the low pass filter. So you understand, in time domain we convolve the low pass filter, the impulse response of this low pass filter with this, right, to get the upsampled signal. So I hope that's clear to you. Here Gn is the impulse response of a digital low pass filter, ideal response, right? So x prime of n, which is the upsampled version of x of n, can be written as the upsampled, right? xun upsampler, right? Convolve with the impulse response of this low pass filter, so that we can write it like, right, using convolution sum formula. So we can write xu of l, right, and this whole thing. Okay, now xu of l, as can be seen from the previous slide, is equal to summation k running from minus infinity up to infinity, x of k impulse of L minus KL. That I think you are familiar with this equation, because we have already done. Now because so that's also because if we solve it, we get, first let's take x of k out, right, and this interchange of summation. So we have summation k running from minus infinity up to infinity, x of k, and then we have L running from minus infinity up to infinity, and we have impulse of L minus KL times G n minus L. Okay, so again that's for the impulse, and you understand its value equals to 1 when its argument is 0. So the argument will be 0 when L equals to KL, right? So in that case this will be 1, so Gn minus L can be written, right? Because the product will always be 0 except when the argument of impulse is 0, and it will be 0 only when L equals to minus K capital L. So that means when when small l equals to K capital L, this will be 1, and here we can again replace small l with K capital L. So this whole thing reduces to Gn minus KL. Okay, so then we have K running from minus infinity up to infinity, x of K, G n minus KL. And because this is G is basically impulse response of this low pass filter, and because of its ideal low pass filter in frequency domain, it has response like this, so its impulse response will be a sinc function in time domain. So that means we can replace it by this. So thus we can convolving the x of K with the sinc function, we can get the output, which is the upsampled version of the input signal x of n, which we also called interpolator. So we'll quickly go through these slides because you have done the interpolator and you have also done the decimator. So how you can increase the rational rate conversion, right? So by combining interpolator and decimator in series, we can change the sampling rate of digital signal by the rational factor L by M. To avoid aliasing, interpolator should always be placed first in the series connection, right? So from x1 of n, we interpolate, then we use a low pass filter, then we use another low pass filter with cutoff frequency. Here we have because we are downsampling it by a factor of m, so it will have the frequency cutoff frequency pi by m. I think these derivations we have already done, so we'll just straight away go and then we downsample it by a factor of m. So if L is greater than m, sampling rate is increased, and otherwise it will be decreased, right? So I hope that's straightforward for you, but still if you feel any confusion, you can ask me in the live session. So these are some of the examples I would like you to go through, and if there is any typo mistake, you can inform me. So I hope that's all for today. So see you in the live session. Allah Hafiz.